principle of exponential equality is a very useful tool in solving certain kinds of equations involving logarithms. We can see this principle here. B to the m equals b to the n is equivalent to m equals n for certain values of b that are not special, such as b equal to -1, 0, or 1. And essentially what this is saying is that if you have two exponential expressions and they both have the same base, in this case b, but if they both have the same base, then we can set the exponents equal to each other, and here we've got m equals n. So let's see how this plays out in a number of examples. One other tool that we'll be using is the equivalence between log and exponent forms of an equation. And let's just write that equivalence explicitly. So the log form of an equation is that if you have some value m is equal to log base a of x, that is equivalent to the equation in exponent form, which is a base a raised to the power m is equal to x. So let's take a look at our first example here. We have y is equal to log base 3 of 1/27th. And the first thing that we want to do is convert this log equation into an exponent equation. So we have the base is 3, and we will write that base, so base, which again is 3, raised to the power, which is that isolated value, in this case y, is equal to the value inside the log, which we sometimes call the argument. So that's 1/27th. What we're aiming to do is to have two bases that are equal to each other. And in this case, the base on the first expression is 3. So we would like to have a base of 3 for the 1/27th. And we can rewrite 27 as being 3 raised to the third power. So this now becomes a fraction 1 divided by 3 to the third. Well, we're getting closer. We have bases of 3, but in order to have this base of 3 in the numerator, we need to change the exponent. So when we bring it to the numerator, we will change the exponent from positive to negative, and now this becomes a -3. And what we see now is that these two bases are alike. We have 3 to the y is equal to 3 raised to the -3 power. And because the bases are the same now, we can just set the exponents equal to each other, and we have the equation that y is equal to a -3. So we have solved this equation by, first of all, using the conversion between log form and exponent form, and then secondly, applying the formula that if bases are same, the exponents can be set equal to each other. Let's take a look at another example. So we have y is equal to log base 10 of 0.001, which you can call 1,000th. And what I'd like to do is to, again, convert this into exponent form. So the base is 10, and the power is the isolated value, so that's y. So we have 10 to the y power is equal to 0.001, which if we write it in its fractional form becomes 1/1000th. And again, what we are aiming to do is get the bases to be the same. So when I have a base of 10 on the left, I also want to try to change this fraction into a value which has a base of 10. 1,000 we can call 10 to the third. And again, we will change this positive exponent to a negative exponent, 10 raised to the -3, because we want to move it from the denominator to the numerator. And just like before, when we set the two powers equal to each other, we get y is equal to -3. So just to look back at these two problems, we see that changing to exponent form allows us to use this property of exponential equality, but we also want to make sure that our bases are not the forbidden numbers, which in this case are -1, 0, or +1. And we see that in both cases it's not the case, that in one case our base is equal to 3, and in the other case our base is equal to 10. Let's take a look at another example. As before, we will change this log equation into an exponential equation. So the base is 2. The power, which is the isolated term, is -3, so we have 2 raised to the -3, and the argument, or the inside of that log, is equal to x. And now our x is isolated, so all we have to do is work out this expression, 2 raised to the -3 power. We convert to a fraction, 1 divided by 2 to the third, and we end up then with 1/8. And so solving, we can see then that x is equal to 1/8. A similar example, we have x as the argument of this log, so we take the base, which we will use. So we have 32 here, that's the base for our exponential equation, raised to the power, which is the isolated expression 2/5, is equal to the inside of that log, or the argument, which is x. Now when we want to simplify this exponent, we can do it a number of ways. One is to realize that 5 in the denominator means a 5th root. But I think that a simpler way to solve this is just to realize that 32 can be expressed as an exponent. And if you're not sure exactly what its value is going to be, we can break 32 into 4 times 8. And 4 you can continue to break into prime factors as 2 times 2. 8 is 4 times 2, which will be 2 to the third, or 2 times 2 times 2. So now this value of 32 we can write as an exponent. We can write it as 2 to the 5th power. However, over here we have an additional power, so we've got power to a power, so 2 raised to the 5th, and that whole thing is going to be raised to the 2/5 power. And whenever you've got power to a power, you should multiply the exponent, so we're going to multiply 5 times 2/5. And we can see that the numerators, 5, that numerator of 5 will cancel the denominator of 5, and we just get 2 raised to the 2nd power, which is equal to 4. Let's take a look at our last example. So again, we're converting this log equation into an exponential equation. Base is 5, raised to the power, which again is the isolated value, is equal to the argument, the inside, which is x. And so again, x is isolated, and all we need to do is take 5 to the 0 power, which is just equal to 1. Looking back at these 5 examples, in the first 2 examples, we see that when we converted from log form into exponent form, we were able to get 2 expressions that had the same base, and then we were able to set the 2 exponents equal to each other. But in the last 3 cases, when we converted from log form into exponent form, we simply had an expression to simplify, and that allowed us to get to our solution.